Hello and welcome. My name is Amanda Olson, and this is part 2 of the discussion on derivatives and looking at the derivative of a function. So in the previous video, we looked at the graph of the function f of x equals x squared plus 1, and we talked about secant lines for that function. And we talked about how the closer in x values you have, the more the secant line represents the tangent line. And we concluded that to find the tangent line, which is when the secant lines are points of x that have x values that are the same, or in other words, the same two x values. We can't actually choose the same two x values because that slope, if you have the same two x values, your difference in x values will be 0. And so your slope, you have a denominator of 0 and you can't have that. So we said the next best thing is to look at the limit as you choose x values that are closer and closer together. Or in other words, looking at the limit as delta x, that change in x approaches 0. Now, I've said this to my students before, but if you don't like the delta x symbol, some textbooks use the letter h, and h again is just that difference in x values. Okay, so you can think of that on a graph of a curve. You have a initial x value, and then you have x plus h that lies h units from your initial x value. And then with each of those, you have your corresponding y values. And we use x and h so we can generalize it, where you have a general function that you can input values into. And this function is called the derivative. So this f of x plus delta x, this is sort of like our y2 minus our y1, and then all together over, this is my difference in x values. Or what we could also call, if I take x plus h, subtract x, this is equal to the limit as h approaches 0 of f of x plus h minus f of x. All together over, the x's will cancel and we're left with just h. So you don't have to use h, you can use other things, but the most common notation is to use delta x and h. Again, I'm going to do this without proof, but I just wanted to work at least one of these and show you how to find the derivative function, derivative as a function for a given function. So if I have the function f of x equals, getting all kinds of messy here. If I have the function f of x equals x squared plus 1, I'm going to end up just kind of filling in some of these parts for my graph. So one of the things is I'm going to need f of x plus h, that function. We're given f of x. We already know f of x, so we don't have to find that. And then h is, just given to be h. Again, that's not really interesting. We already just know the variable h. So we want to find each one of these parts and then input them into our limit. Okay, so we're going to look at the limit as h approaches 0. And then we need each one of these parts to fill in. And so the current thing I don't have is I don't have my f of x plus h to complete this table. So I want to find that for my function. And it's going to differ depending on which function you look at. So f of x plus h, for this particular function, we're going to take our input, x plus h. We have it squared. And then we'll add 1. And then we need to simplify. So you want to remember to recursively distribute or FOIL or, you know, when you square that x plus h, you're squaring a binomial, so you have to recursively distribute or FOIL. And when you do that, you get x squared plus 2xh plus h squared. If you get stuck here, pause the video and look up FOILing, or send me an email and I'll work on that with you. But this is what we get when we expand and then combine like terms for f of x plus h. So I'm going to put that right here. For f of x plus h, we have x squared plus 2xh plus h squared plus 1. And then we have this, and then we want to subtract our f of x. And again, we already have our f of x. I am going to use parentheses though, because I can see that my f of x is going to be 2-term. And so using parentheses will remind me that when I'm subtracting a 2-term, I need to distribute that subtraction. So then I have x squared plus x. And then we also have h. And h is just equal to h. From there, we just want to continue on and simplify, combine like terms. So then we get the limit as h approaches 0. I'm going to combine like terms and simplify some things. I have x squared plus 2xh plus h squared plus 1 minus x squared minus 1 all together over h. From there, we can combine like terms. So x squared, we're still looking at the limit as h goes to 0. It's important we don't drop that notation because each line, it is the limit. Otherwise, they're not necessarily equivalent. X squared minus x squared, that's a 0x squared. We have 2xh, no like terms with it, so it stays there. We have an h squared with no like terms. And then we have +1 and -1 that are like terms. They combine to give us 0. So then we have all of this over 0. This next step you can then factor out. So we're still considering the limit. Direct substitution doesn't work for this particular problem. So we can't directly substitute 0 because we get a 0 over 0 form. So direct substitution doesn't work, but we're going to see we can still evaluate this limit. And when I evaluate this limit, I'm going to first factor out h from the numerator. And then we see that the numerator and denominator have a common factor of h. And we like to just say, okay, cancel h. Technically, we can't cancel h because h could be 0. So we make the case, okay, we know h is not equal to 0. So then when h doesn't equal 0, this initial function is going to agree with the function 2x plus h. And so we have two functions that agree at all but one point, the point where h equals 0. And so we know then that their limits are going to be equal. That's a theorem that we've previously established. Now, the nice thing about this new function that I'm considering is that direct substitution is possible for it. So 2x, and then I can substitute 0 in, and I get 2x. And the derivative is defined to be a function, so this is reasonable. Really, you know, your slope of your tangent line is going to change based on where you are on the graph or what x value you're working with. Okay, so if we consider, well, if you go back to that previous graph, you're going to see, you know, you have different tangent lines for different parts of the curve. So if I have this graph right here, this tangent line is very different than maybe what I would have if I looked at the tangent line kind of at a point here. Okay, the slope of each of those lines varies. And so the function, it's a function because it's varying. Unless you're dealing with a straight line, the slope for a curve, the instantaneous slope, the slope of that tangent line is going to vary depending on where you are on the graph. So hopefully this gives you a little bit of information on how to find the derivative for a function. As we progress, you're going to see other ways, some kind of shortcut ways for finding the derivative. I think that's great, and we will definitely use those shortcuts, but where we are right now, you're gonna wanna pause and not use those shortcut methods until we get to the point where we're gonna work those, until we discuss them. So you are going to wanna make sure that you're able to find the derivative using the limit definition, because that's something that will show up, that I'm gonna assess in my class. We have some other notations for derivatives depending on where you're working. So long story, calculus was developed by two mathematicians, Leibniz and Newton, and communication wasn't instantaneous like it is today. It was slow. So you have one person developing calculus, another person developing calculus, and they were kind of maybe rivals. And so we don't know who actually invented calculus, because they both were kind of working on some stuff, and then it both kind of came out around the same time. And because communication was so slow, it's really hard to pinpoint who did it first. And that's just something, maybe they both kind of did, or maybe one of them copied another person. We'll never know. But what we can say is we have with it two different notations. And so we have the Leibniz notation and the Newton notation, and each one of these are different ways of representing that derivative function. So we have f prime, the derivative of y with respect to x, y prime, d dx, and then this d sub x of y, that's the derivative of x, the derivative of y with respect to x. You kind of have some varying notations, and depending on the context, you just want to be familiar and recognize that those are all the same things. And we'll explore that a little bit more as we go too. All right. I don't want this video to be too long, so I'm going to stop here. Thank you.